Hello. Very good evening to you all. Hello. Are you getting me? Okay. Okay. We'll wait for 2 minutes more. Then we will start. Okay.
நினைச்சு நினைச்சு பேசாதீங்க முடியலமா என்னால. நீ எதுக்கு என்கிட்ட உங்க போனை என்கிட்ட கொடுங்க? என் போனை நான் பேசிட்டேன். உங்களை பத்தி தான் என்கிட்ட புலம்புறான் அவன்.
Okay. I should start now. It's already 6:05. Okay. My screen is visible to you all. Is my screen visible? Umer, is my screen visible? Kaushik, Sumant. Okay, let's start. Today I will a live tutorial on manufacturing process, that is casting and joining. It is week number 3. I will be discussing here for some of the left out portion of the casting and the starting portions or introduction portion of the joining. I think you already have studied the lecture series from Professor Kumar Choudhury. Okay, whatever I decided that today I will start with some MCQ questions with some basic knowledge. Then I will go for advanced numerical questions. So let's start begin with some basic numerical questions. First of all, I will start some basic level questions and answer. Okay. The first questions appearing in your screen, uh, you all of you just read the questions. Okay. The first questions. Question number 1. Uh, First, a statement is given here. Cell molding is an expandable mold casting process. Statement number 2. Centrifugal casting is a permanent mold casting process. Okay. There are four options. Only options 1 is correct. Option 2 is correct. Both A and B are correct. Both A and B are incorrect. So before solving these questions, you should know the classifications of the casting. What is the classifications of the casting? We can classify it into two part. Okay, two parts. One is the one is the expandable molding process. Expandable molding process. And second one is the permanent molding casting. Okay. What is expandable molding casting process? That is when you will like sand mold. Okay. Suppose you are making a mold cavity with sand. Okay. And then we will pour the liquid molten metal inside the sand mold cavity. After preparing the final product, you will break the sand. Again, you will go for the next manufacturing process. But in the case of the permanent mold process, there is a metallic die. You cannot break it. You can produce more than one product or more than one manufacturing process. So just to see the classifications, this is the classifications that two process. One is the expandable molding process and another one is the permanent molding process. In the under the expandable molding process, the sand casting, it is very obvious. Okay, and cell molding. Cell molding also falls under the expandable molding process. And investment casting. Just wait. Okay, whatever I am discussing, that next is the permanent molding process, that you have one metallic die. In this metallic die, you will pour the liquid molten metal. You manufacture more than one product. Okay, you can do more than one product. Like this is the die casting. Already you have studied the die casting and centrifugal casting. It is also a permanent mold made by metallic mold, continuous process. You see, it also comes under the permanent molding process. So our option, what will be the first statement? The cell molding is an expandable molding casting process. Obviously, cell molding falls under the expandable molding process. Okay. So first is the correct, and centrifugal casting is a permanent molding process. Centrifugal is comes under the permanent molding process. So our option, both A and B are correct. C option will be right option. C option is the right option. Both A and B is the correct. I think it is clear to you all. Okay. Next, question number 2. Read the questions here. As the water content in the sand mold increase gradually, okay, you know, during the sand preparations of the sand mold casting, we will add, what is the combinations? Sand and water, sand, water, and some filler. Okay, some filler, I mean additives. Also, you can say additives. Okay, I have already discussed the why the filler or additives is added into the sand with the water. Okay, and some clay is also there. Okay, so based on the questions, what the questions is asking here, if I increase the water percentage, if I increase this water amount, what is the optimum water level of the sand mold casting, green sand molding casting? Do you remember? It is 3 weight percentage. Okay, it is 3 weight percentage. It is the optimum level of the water we will add into the sand with the clay and with the filler additives. Okay, so read the questions. Option A, both the strength and the permeability of the mold increases. Only the strength of the mold increases. The strength and permeability of the mold increase fast, then decreases. Option D, the permeability of the mold decreases. Okay. So what is the correct option? You have studied the XY chart with the water percentage content. Effect of water. Effect of water. Okay. This is the weight percentage moisture. I mean, I am increasing the water content. I am increasing the moisture. Okay. Tensile strength. The tensile strength is in dark black color. Okay. Initially, initially, if I increase the water percentage, the tensile strength is increasing up to almost 3 weight percentage. Then the tensile strength is decreases. Okay. In your questions, tensile strength, I mean strength and permeability. What happens for the case of permeability? Permeability is this is the permeability. This things is the permeability. This graph. Initially, the permeability increases. It also up to the 3 percentage of water, permeability increases. What permeability? Do you know what permeability? After that, the permeability decreases. Initially, permeability of gas bubble generated inside the mold cavity. Okay, gas bubble. Okay, gas permeability. gas permeability. Suppose this is your mold. Inside the mold cavity, this is your sand. This is your sand. Sand is here. This is your liquid molten metal. Okay. When hot liquid molten metal comes in the mold cavity at high temperature, it will form some gases due to oxidation process or reduction process. There are many processes. Some gas bubble is generated. This gas bubble should vent out through the sand mold outside the atmosphere. Otherwise, this gas bubble trapped inside the mold and your casting will be imperfect. Okay, that's why this gas bubble should come outside. Okay, wait 1 minute. Okay, so our permeability, our permeability will be initially the permeability will be high. After the 3 weight percentage, the permeability goes down. Okay, according to this graph, tensile strength versus water permeability. So what will be our right option? So right options will be C. C is your right option. The strength and permeability of the mold increases fast. Increases fast means up to 3 weight percentage. Up to 3 weight percentage of water. Huh. Then decreases. Beyond the 3 weight percentage, what will happen? Beyond the 3 weight percentage, above 3 weight percentage, above 3 weight percentage. This is important questions. Above 3 weight percentage. Suppose this is your sand, lots of sand. Above 3 weight percentage means in between the two sand, there will be the water. There will be the water molecules. Okay. There will be the large amount of the water molecules. Okay. This large amount of the water molecules will increase the density. Okay. Increase the density of the total sand mold. So what will happen? Increase the density. Density will increases. Density will increases. And if the density will increases, the permeability decreases. Okay. Permeability. Permeability. Permeability goes down. Okay. That's why you cannot go beyond 3 weight percentage of water with the sand. Okay. So our C options is the right options. Am I clear to you? Okay. Question number 3. Read the questions carefully. An aluminium plate of 30 mm cross 60 mm cross 10 mm has to be cast in a mold with a mold constant of 12 minutes per centimeter square. The total solidification time of the casting in second is. This is a very simple question from the law of do you remember the name? Chauvinov's rules. Okay. What the Chauvinov's rule says? It says that the time of the solidification time. Okay. Just wait. Chauvin's rules says that calculate that the solidification time. What is the Chauvin's rule says? This is the Chauvin's rule. This is a very simple rule that calculate the solidification time. That calculates the total solidification time. Total solidification time. Solidification time. This total solidification time depends on the liquid molten metal volume and area. Okay, cross section and area. So just put the value here in the total solidification time. So our solidification time Ts equals to Cm. Cm is a constant that is the mold constant. Okay, mold constant multiply volume of the total volume of the liquid molten metal or casting volume divided by cross section area to the power to the power n. When n is not given, then you consider n equals to 2. Okay, when n is given, then you have to take or consider that value. Here n is not given, so we can take n equals to 2. So uh, first of all, this is the mold constant 12 minute per centimeter square. So just a little bit of conversions you have to do. That is the Cm equals to 12 minute per centimeter square. So convert it into second because your question is asking in second. So 12 multiply 60. This is the second per centimeter square. Next is the total aluminum plate volume. So aluminum plate volume V, capital V equals to, we know that length multiply width multiply height. Okay. So length equals to 30 mm. So you have to convert it into centimeter because the mole constant is in centimeter. So length equals to 3 centimeter, multiply width equals to 6 centimeter, and height equals to 1 uh, centimeter. Okay, so this is your total volume 18 centimeter cube, and you have to find out the area. What is the area? How would you calculate the area of a rectangular plate? You have to calculate the area. If you have to consider the area, that is the cross section area, that is the not area, cross section area, this is the total surface area. A is the surface area here, surface area. Okay, this is the surface area, surface area. A is the surface area. So the rectangular plate look like this. This is your product you have to make, you have to cast. So here are 6 surface. This is surface number 1, and in opposite the surface number 2 or 1 dashed, I am writing 2, and this is the surface 3. In opposite, this is the 4 surface, and this is the surface number 5. In opposite, surface number 6. So just to calculate the total surface area equals to 2 multiply first surface, that is the length equals to length multiply width. So 3 into 6 Second is the width multiply height, 6 into 1, and third surface is the 3 into 1. So it is coming 2 multiply 18 plus 6 plus 3. What is the result? Is coming 2 multiply 18, 6, 24, 27. 2 into 27. Okay. So put the all value here. Uh, total time equals to 12 multiply 60 multiply V, volume equals to 18 centimeter divided by 2 multiply 27, and this is your 2. So you just a bit of calculations. Okay. So 12 multiply 60 multiply 9. Okay. So 3, 4. So your answer equals to 4 into 20, 22nd. Okay. So our option A is the right option. Okay. So accepted answer is the 82nd. It is clear? I think it is clear. Okay. Next questions. Question number 4. Question number 4. A cylindrical riser with an optimum volume of 20 centimeter cube has been used for a sand mold casting process. The diameter of the cylindrical riser in should be. What is the function of riser? I have told you that a riser is a part of the molding process that supply the liquid molten material inside the mold cavity just to compensate the shrinkage volume inside the mold. Okay. So the questions is important here. One word is the optimum, with an optimum volume. With an optimum volume means, what is an optimum volume means? Okay. Optimum volume means you have studied that riser, what is the best riser design? Do you remember what is the best riser design? It is the taper riser design. Okay. But for the cases here, it is written the cylindrical riser. You have to design the cylindrical riser. So optimum cylindrical riser, what will be the optimum cylindrical riser? This is your riser, cylindrical riser. Okay. Okay. So suppose this is diameter is the D and height is the H. Height is the H. For the case of the optimum cylindrical riser, you have studied that D equals to H. Already you have studied in this slide that D equals to H. Optimum riser design for the cylindrical case, D equals to H. Okay. So you need a bit calculations that so cylindrical riser with volume V. What should be the diameter of the cylindrical riser? So diameter, what will be the diameter? Your diameter will be, you just calculate a volume. So just wait. So here total volume of the cylinder is the pi by 4 d square multiply d square multiply h, height of the cylinder. But here we know d equals to h. Okay, so just put the value d equals to h. I mean, in place of h it will be d. Okay, so the total volume will be pi by 4 d cube. So this much of volume equals to 20. This is equals to 20 centimeter cube. Okay, 20 centimeter cube. So just calculate the d. So just calculate the d. So 20 multiply 4 divided by pi. This is the cube root. Okay, so just to calculate these things. Okay, the answer will be coming around 20, exactly not 20, 29, but it will be coming 29. Okay, so your accepted answer is the 29. C is the correct option. Okay, next is the question number 5. Typical machining allowances for sand casting range between. This is a, you have to remember these kind of questions. Okay, for sand mold casting, the different allowances like machining allowances, shrinkage allowances, draft allowances you have to provide it. Okay, so what is the draft allowances? You know that like 0.5 to 2 degrees draft allowances you have to provide it, or 1 to 3 degree. Okay, so but machining allowance you just write the option will be 1.5 to 3 machining allowances. So for the case of the machining allowance, for machining allowance, for machining allowance, the allowances will be false 1.5 to 3 So our correct accepted answer is question number B. Next, question number 6. Casting defects like hot tearing and cracks in the casting may occur. This is very important. You just go through before any exam casting defect. At least one question in any examinations you are going to appear. Casting defects, one question will come from the casting defects or welding defects. Okay, so you have to remember the casting defect hot tearing. Hot tearing means question number answer at sharp corner of the casting, A thick sections at intersections, at thinner sections, D when the pouring temperature is high. So let's see what is the hot tearing. So this is the hot tearing. When suppose basically hot tearing, suppose you were going to design like a I section casting, I section casting. Okay, basically what happened? Basically what happened? In outside the sand is there. Okay, outside is your sand. Sometimes what happen during the plain sections it will not affect, but for the case of the corner, okay, or at the sharp edges or sharp corner like these things, okay, in this portion, what will happen? The sand is restricting the shrinkage of the liquid molten metal during solidification. So sand is restricting the shrinkage of the casting, restricting the shrinkage shrinkage of the casting of the cast. Okay. So what is happening? The sand is exerting or pulling the liquid molten metal. So there will be a tearing like these things, a gap like this. It will happen. Okay. 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 So our correct option is the at sharper corner of the casting, this tearing kind of thing will occur. So question number 7. This is the questions from the welding. In welding, the atom of two metal are considered to be bonded. You know that welding is a permanent joint, that two metal is joined or fused by the welding process. Okay, what is the principle behind this fused together or bound together or bond together? So, statement 1, when the net potential energy is maximum, when the net potential is minimum. Question number, statement 3 is the net bonding force is zero, net bonding force is maximum when the attractive force is maximum. So you have studied one graph by professor. This is the graph you can study mechanism of the welding. What is the mechanism of the welding says that there are two forces. One is the attractive force, attractive force, and another one is the repulsive force. Okay, attractive force and repulsion force. And when we take the resultant of this attractive force or repulsive force, the net force come into play. So the graph says that the at the welding positions, the net force is zero. This is the position. When the attractive force equals to repulsive force, then the permanent welding joint will occur. So net force equals to zero. So net bonding forces equals to zero. Of this is the correct option. Okay. And in the next graph, you can say the net energy. Net energy when the net energy is minimum. Okay. So net bonding, so when the net potential energy is minimum. So option 2 and 3, these option 2 and 3 is correct. You just study the graph carefully. Okay. So our option 2 and 3 is the correct option. So B is the correct option. Okay. Is it clear? If you have any doubt, you can ask me. The mechanism of the welding, how the mechanism of the welding happen? The two molecular level, when it comes very close, then what will happen? The outside there are electron flow, electron is there. The two atom when comes closer, the this electron will repulsion, the repulsive force is acting, and simultaneously when we when this molecule or atom is come closer, then this electron and inside the nuclei will get attracted. So repulsive force and attraction force both will play. But during the equilibrium positions, this attraction force and repulsive force is both will be, the net forces will be zero and kinetic energy will be minimum because it is very equilibrium state. Okay, so our option 2 and 3, net bonding force is zero, net potential force is minimum, so option B is correct. Okay, question number 8, the welding process used for joining material that cannot withstand high temperature is, you have to give the example of the welding that cannot withstand high temperature. Basically, what we know that welding is a process of bonding two material either by the applications of the external pressure, or by the temperature. Okay, what the temperature and pressure do? This temperature and the pressure, applying the external pressure and temperature, the two material will be fused together. Okay, then it will make one shape. Okay, so two material will form one material. This is the welding definition. And just look at the answer. The solid state welding, liquid state welding, generally you know that the liquid state welding, solid liquid state welding, and ultrasonic welding. Okay, so cannot withstand high temperature. So at low temperature, at very low temperature, very low, no, at low temperature, what kind of soldering, what kind of welding is there? So for the electronic parts, you just use for the soldering process. This is a soldering process. Suppose this is your circuit, electronic circuit, okay, capacitor or resistance. Okay, you just take one where you just take a very low melting point wire and you just melt and fuse together. Okay, so this is the solid state and the liquid state. So option C is the correct, that at low temperature, solid and liquid state. So our option C, solid and liquid state welding, is a example of low temperature welding processes. Okay, it generally very useful or applicable in the electronic industry like soldering process. So you can just see the definitions or classifications of the welding. There the solid state welding. First one is the solid state welding. This solid state welding generally example of the friction welding. Okay, just you will study just two material. You just rub each other and temperature will generate it and you just apply some pressure and it will automatically fuse together. Okay, so this is, there is no melting occurring, so this is the friction welding type. This is solid state welding. Liquid state welding, you already know that gas welding, resistance, arc welding, these are the all liquid state welding. That means that in between here the liquid will form and this two liquid will fuse together, the one and two part. Okay, and next is the solid liquid state welding. This is the example of the brazing and the soldering process. Okay, so this is the solid and liquid because one part is the solid state and another part just you melt and you add some wire. Okay, for connectivity. So our option C is the correct. Okay, next is the question number 9. There are four statements. Statement A, in a welded plate the weld area remain in high residual tension and the base metal is in compression. In B, welded plate, the welded area remain in compressions and the base material is in high residual tension. In a welded plate, both the weld area and the base metal remain in high residual tension. In a welded plate, both the weld area and the base metal remain in compression. So, what will happen? Suppose you have two metallic sheet. Okay, by using the arc welding or gas welding, you just melt this portion. Okay, there will be the melting zone. Another one is the heat affected zone. Okay, and third zone is the cold state zone or parent material, whatever it is. Okay, so what will happen after the welding? There is the development of the residual stress. This is the residual stress. Residual stress is very important. During any heat treatment process, there may be the residual stresses, formations of the residual stresses or residual stresses. Okay, residual stress. So this residual stress is a negative, has a negative impact on the welding or any kind of mechanical parts or any kind of structural parts. Always we want to avoid or always we want to remove this residual stress. Okay, otherwise this residual stress may damage your material or structure. Okay, how it is damaged? Just just you see the example here. This is the welding zone. This is the welding zone. In the welding zone, it is a very high temperature, liquid molten conditions. So what will happen that it will be in tension because high temperature, it will be in tension. I mean, the liquid wants to flow outside or it will be in tension conditions. But this is the cold zone that it will be in compression state. So inside the liquid molten metal zone or inside the welding zone, it is in tension zone. So stress is positive direction. Okay. The stress tension, you know the tension. This is the force opposite directions. F and compressions, you know that this is the directions of the compression force. This is the compression force. This is the tensile force. Okay. So this is the in between tension and subsequently the two side portions of the welding zone, it feels compression force. This is the compression force, this is the tensile force. So some part tensile force, some part compression force. This is called the residual stress. I mean stress inside the material. Okay. So our option A is the correct. Only so first one is the correct. Okay. Welded zone is the high residual tension stress and base metal is in compression stress. Because why the base metal is in compression stress? Because base material is in room temperature or temperature is less. Okay. And this is the tensile because the temperature is high. If you have one rod, you just heat this rod, what will happen? The extension of this rod will happen. Okay, I mean the elongations will be happen. So elongations, how the elongations is there? It is only because of the tension between the two molecule. The molecule is in tension. So tensile and compressions in the same structure, this is called the residual stresses. Okay, so we have to reduce the residual stresses or remove the residual stresses for any structure. So our Questions number 10. Question number 10. In the heat affected zone, near the weld interface of a welded joint, the grains are finer grain, coarse grain, or columnar grain, or finer and columnar grain. So, what will happen? Suppose this is your two material. You wants to just wait. Someone is okay. So, what will happen? Suppose you wants to join 1 and 2 by welding process. So, this will be your melting zone, and this will be in melt conditions, liquid conditions, liquid conditions, and just beyond the liquid, it will be heat affected zone. So it is in not in liquid zone, but the there is the rise in temperature. So it is called the heat affected zone. Okay, heat affected zone. So what is the changes in the grain in the main inside the welding portions and heat affected zone and outside the parent material? Okay, there are three zones. One is the welded zone, welding zone. Second one is the heat affected zone, heat affected zone, and third one is the base material. So what is the grain structure or the change of the grain structure, microstructure will change according to the applying heat or due to the heat flow. So inside the welding zone, this is that this is the columnar grain structure will there. What is the columnar grain structure? It is like this way. Okay, and just see the diagram. This is the columnar grain. This is the welding joint. Why this columnar grain is appearing there? Because anyone could say why the columnar formations or microstructure is forming inside the welding portions, because the it is in high temperature or liquid molten material. You already studied it in the casting process also. Okay, when the heat transfer rate is very low, or heat transfer rate heat transfer rate heat transfer rate heat transfer rate low, and that means solidification's time is very high. Solidifications. So solidification's time is high. There is a very high chances. There is a enough time to make the grain growth. That grain growth means that columnar structure grain is very high. Okay, this is the grain growth like this. The grain has enough time to grow. Okay, so this columnar type of grain is forming. Just below, there is the porous surface, porous grain. I mean a little bigger. Okay, porous. This is the porous because the heat transfer solidification time is little less, okay, because the temperature is low, okay, and just below just below this is the finer grain. I mean, why the finer grain? The heat transfer rate is very very high. As you studied in the casting process, the sand, the surface of the sand, the heat transfer rate is very very high. That means solidification time is very high. So the finer grain will form when the solidification time is less or heat transfer rate is very very high. In this portion, the very finer grain is produced. Our question is asking the near the heat affected zone. So our heat affected zone or near the weld interface, just weld interface. So columnar grain, then the weld interface. So interface, this is the core structure. So our option B is the core structure. Okay. So our accepted answer is the B. Okay, this is the chorus. I think it is clear. Next, I will go some advanced level uh, numerical or questions answering sessions. Okay. I think, is it clear? Whatever I discuss the questions now, I think, is it clear to you all? Kosik, Umer, Syed, Siri. Yes, yes. Good evening. Parvinder Kumar, Parveen Kumar. Yes. Yeah. Should I go to the next advanced level numerical or discussing question answer discussing part? Okay. So this is the live question sessions for some advanced level question. So here question one, question one. Just read the question. In a welding, a mild steel sheet using an oxyacetylene flame, the total amount of acetylene consumed was 8 liter. The oxygen consumption from the cylinder is 8 liter, 16 liter, 20 liter, 24 liter. How could you solve these questions? So before solving these questions, you must know the flame or type of flame. Okay. So this is a flame is generated with the help of the oxyacetylene flame. Okay. So and this oxyacetylene flame, which material is going to uh, weld? You are going to welding mild steel. Okay. So your mild steel you are going to, okay, mild steel you are going to weld. Okay. So let first just I am going to discuss the oxyacetylene flame. When the acetylene gas is completely in combustion, Now, what is the equation? So, this is the acetylene gas formula C2H2. This is in gas condition. This is very, very important. Plus 5/2 O2 and 2 molar carbon dioxide. This is also in gaseous conditions. Plus this is water vapor. This is in gaseous conditions. Okay. So from this reaction, you can easily understand that. So 1 mole acetylene C2H2 is completely combustible form with the help of 2.5 times 2.5 times oxygen. Okay, this is the complete combustion. This is the complete combustion. Complete combustion. Okay, but here the question is, okay, but you can easily answer that. The 8 liter acetylene, that means 8 liter acetylene. 8 liter acetylene, oxygen required just 8 multiply 2.5. 16, 16 20. But this is wrong. Here the question is asking not the complete combustion, but the question is asking the oxygen consumption from the cylinder. Oxygen consumption from the cylinder during the mild steel welding. You have to remember, for the case of the mild steel welding, there are the three type of flame, oxyacetylene flame. First one is the neutral flame. First one is the neutral flame. Just I have. First one is the neutral flame. This is the neutral flame. And second one is the oxidizing flame. Third one is the carburizing or reducing flame. This is very, very important. Three flame. Generally, questions also will come from this flame. What is the core temperature of the neutral flame? Sometimes they ask. Okay, sometimes they ask different temperature core, oxidizing flame. What is the color of the flame? These type of questions will come. Okay. Uh, neutral flame means ratio 1:1. Oxygen and acetylene ratio is 1:1. And oxidizing flame means acetylene acetylene suppose 1 liter acetylene, so 1:2 acetylene you required, oxygen you required more. This is the oxygen is more than 1:1. Okay, oxygen is high. And the carburizing flame, this is the ratio is the, suppose this is 1 liter acetylene is to less than 1 liter oxygen. So for the case of the reducing flame or carburizing flame, it is the below 1 liter of the oxygen. So in this case of the carburizing flame or reducing flame, the oxygen percentage will be less. For the case of the oxidizing flame, the oxygen percentage will be high. and neutral flame 1:1 ratio acetylene and oxygen ratio. But most important is the when we'll use the neutral flame, when we'll use the oxidizing flame, and when we'll use the carburizing flame. In your question, it is given that the mild steel using the oxyacetylene flame, but which flame will going to use? Then only you can answer. For the case of the mild steel, we'll use the generally neutral flame. So neutral flame means 1:1 oxygen to acetylene ratio. So when acetylene require 8 liter, our oxygen requires also 8 liter. So 8 liter oxygen will come consumed from the cylinder. So our option A is the right option. Okay. For your information, just I am discussing that the for oxidizing flame, which cases the oxidizing flame require? Generally, the oxidizing flame requires just to weld the alloy. Okay, alloy kind of material like brass, bronze, these kinds of material when you going to weld, the oxidizing flame require. And carburizing flame is required when you going to weld the cast iron. Okay, cast iron or high carbon steel. This is the high carbon steel cast iron. Cast iron. Okay, or high carbon steel. This is very informative questions. You have to understand. Okay, so and you can see for the neutral flame, the inner core is the 33 degree 100 degree centigrade and outer envelope 1260 degree centigrade. The inner core, and for the case of the oxidizing flame, you just pointed inner core. Okay, pointed inner core, and the carburizing flame or the reducing flame, it is the bright luminous inner core. Okay, you just see the difference. This is very important for your information. So our options, A is the right option, and you just remember the acetylene oxygen combustion reactions. For the complete reactions, you required 2.5 times of oxygen, 2.5 times oxygen than the acetylene. But for the welding case, you have to understand which type of flame is used for which type of material. Generally, neutral flame is used for the mild steel, and high carbon steel, this is the reducing flame or carburizing flame. And the reason is written here, just to prevention of the oxygens and control carbon content and the reducing brittleness. Okay, am I clear? Is it okay? Are you getting me? Okay. Our next questions. This is also a combined numerical questions. So common data questions. A weld is made using MIG welding process with the following welding parameter. This is from the MIG welding. Okay, this is the MIG welding. Uh, this is the MIG welding. for your basic understanding that the two material is joining with the help of the MIG welding. Okay, suppose this is the first material and this is the your second material, and okay, and welding is done along this length. Okay, this is the welding portion. Okay, uh, this is the welding portion. Okay, so the following MIG welding this is, and here the current I, here current I equals to 200 ampere and voltage V equals to 25 volt, and welding speed that is the V weld welding speed is 18 centimeter per minute, 18 centimeter per minute, and wire diameter, there is one wire we are using just to provided the external material. This wire will be fused and or melted, and this melting of the wire will join the two material. Okay, this is the wire. This wire diameter is the diameter of the wire. The diameter of the wire is 1.2 mm, and wire feed rate when the wire will join. Sorry, where the wire will melted, it will fused. Okay, the and will supply the where will consumed. Okay, so where feed rate is the where feed rate where equals to 4 meter per minute, 4 meter per minute. Thermal efficiency of the process, thermal efficiency of the process is 65%. That means 0.65. Okay, question is the heat input per unit length of the weld in kilojoule per centimeter is A, B, C and D. So what is the heat input? You have to calculate the heat input. Okay, what is the reading here showing that I equals to 200 ampere and V equals to 25 volt. Okay, this is the energy is you are giving from the meter, electric meter, but there is some efficiency, not the total energy is not using for the welding purpose. Some amount the heat is losses. Okay, that's why the efficiency is given here. So if we formulate the efficiency formula, okay, you just write down the efficiency formula. So I'm going to the next phase. Okay, efficiency formula. Right. Okay, what is the efficiency? Thermal efficiency. This is the thermal efficiency. So can we write that the heat, the rate of heat supplied, the rate of heat supplied, rate of heat rate of heat supplied divided by rate Rate of heat generated. Rate of heat generated. Rate of heat generated means this is the your input. This is your input, and your but this heat supplied to the welded. This heat supplied to the welding. You are giving. You are generating heat from the electricity. You are generating heat from the electricity is the I equals to I multiply V, and some of the heat is loss, and some portion of the heat is uh, exactly using for the melting purpose of the during the welding purpose. So rate of the heat supplied I multiply V, sorry, what is the supplied? So we can say that the H S or H G generated. So can we write that heat generated input? So HS equals to thermal efficiency multiply Hg. Heat generated means what is the total heat your from the electricity is coming. So efficiency 0.65 multiply total heat I multiply V 200 multiply 25. So this is coming 500 watt or joule per second. Joule per second. Okay, is it clear? So the total supplied heat is, sorry, you just calculate. It is not 500. It is 500 multiply 0.65. It will coming that 3250 3250 joule per second. So heat supplied. So H dot S 3250 joule per second. This much of heat is supplied in the welding portion. Supplied to the these welding portions. This much of heat is supplied. You are exactly it is utilizing for the melting of the material. Okay, but you are giving from the electricity 5000 5000 heat, 5000 joule. This is 5000 joule per second or what? But how much amount of the heat is utilizing heat or utilizing heat is the 3250 due to the thermal efficiency. Some heat is loss. Okay, due to the thermal efficiency. This is the thermal efficiency. So our effective heat is or supplied heat to the welded is the 3250 heat. So your answer questions is the heat input per unit length of the weld. Heat input per unit length of the weld. Heat input per unit length of the weld. So welding speed. So what is the welding speed? That means the welding speed is in these directions. Okay, in these directions welding speed. Okay, the welding speed is uh, welding speed V weld 18 centimeter per minute. So welding speed is V dot weld equals to 18 centimeter per minute. Okay, so if you calculate, if you convert it, the heat supplied, that is the 3.2 kilojoule per second, kilojoule per second. So your heat input per unit length will be the heat input per unit length. So our heat input per unit length equals to total supplied heat. How much? That is the H dot S divided by V weld. Okay. So it is 3.2 kilojoule per second divided by 18 centimeter per minute. So you have to convert that 3.2 divided by 18, upper side it is 60 for the second, because your answer is, you have to answer it in second. So your answer will be coming that 10.83 kilojoule per second. So 10.83 kilojoule per second. So our option C is the correct option. Okay. In continuations of the questions, question 3. Okay. The question 3, the area of cross sections of weld bed is mm. What will be the answer? So cross section area of the weld. Okay, you have to find out the cross sections area. That is the cross sections area. You can find out that this is your two metal. Okay, this much of area, suppose you are welding. So this cross sections area you have to find out. Okay, this plate is extended actually. Okay, this is in 3-dimensional. Okay, this is in 3-dimensional. Okay, so the area cross sections of the weld bed is mm square. So how can we calculate? We can calculate from the wear diameter and wear feed rate. Wear diameter and wear feed rate. How much volume of the molten material is melted from the wear? Okay. So we can calculate the molten material, the molten metal is consuming from the wear. Okay, the volume of the volume flow rate. So total volume flow rate means that volume flow rate from the wear. So consumed consumed molten wear equals to pi by 4 multiply wear diameter multiply length. Okay, you have to put the length. That length is wear feed rate. That is the 4 meter wear feed rate. Okay, wear feed rate of the wear. This is in rate because per minute it is coming. Okay, so you have to convert it per minute, means that the per second if you convert, just pi by 4 wear diameter is the, what is the wear diameter? You have to convert, wear diameter is 1.2 pi by 4 d square. This is the d square, 1.2 square multiply feed rate is the 4 meter. 4 meter means that the 4 multiply 1000, it is in millimeter, and per minute, minute means in second. If you calculate this, you will get the total consumed molten wire, that is the wire is in melting form, and this melting wire is fused the two plate. Okay, so it will give that, you just calculate, I have calculated, it is giving 75.36 mm cube by second, per second. Okay, so but our area of cross sections, but we have to calculate the area. Here the wire is consumed, okay, in this way, but you have to calculate this area. So what is the area? So what is the area? So this 75 75.36 equals to per second area of the weld multiply velocity of the weld. Okay, because in this velocity of the weld, v weld. So 75.36 equals to area of the weld, you have to find velocity of the weld is the 18 centimeter. That means 18 centimeter multiply 10, it is in millimeter, and 18 centimeter per minute. Per minute means you have to 60. And if you calculate the area of the weld, and you will find out the value, that the 25.2 or 25.12. Okay, this is mm square. That means this area, this area, this area, this weld area is the welding area. Okay, so our option B is the correct option. Is it clear? Kosik, Shayad, Umer, is it okay? Are you getting me? Okay. So our next question is, this is your next questions. Question number 4. Read the questions. In spot pulse laser welding of aluminium plate, the density 2700 kg per meter cube, specific heat 896 joule per kg, melting temperature 933 Kelvin, latent heat of the melting is 398. I think anyone is coming, wants to join. Ashish Jadhav. And the at a temperature of 30 degrees centigrade, pulse with energy of 0.5 joule is focused onto an area of 0.05 mm square, because it is a laser welding. So focused area is very small. Okay, if the entire energy is coupled into the material, what will be the depth of the weld, assuming the cross section area of the weld is circular and is uniform throughout its depth, only conductions in the directions of the penetrations. So uh, what is happening here? So aluminum plates is joining. So suppose this is your two aluminum plates is joining. Okay, this aluminum plates density is given that density of the aluminum plates 2700 kg per meter cube. Specific heat that is the CP 896 joule per kg. And melting temperature T melting, that is the in this temperature aluminum plate will be melted 933 Kelvin. Aluminum plate will be melted. Latent heat of the melting, during the melting the latent heat is the this 398 kilojoule per kg. You just remember that this is kilojoule, this is joule. You have to convert it. Okay, during the question solving or during the calculation process. And initially, the initial temperature is the room temperature, that is the T atmospheric temperature, T ATM temperature is the 330 degree centigrade. That is in 30 degree centigrade means you have to convert it into Kelvin, or okay, you just add 273, that it will coming 303 Kelvin. Okay, pulse with energy. This is for every cases, any numerical problem you are going to solve from the welding process, you have to calculate the energy and how much energy is coming from the electric meter or electricity, and how much amount of the energy is utilizing for just to melt the material during the welding. These calculations you have to calculate. In between, whatever the losses is going for the, you can consider it as a efficiency. Okay, so here energy pulse with the energy equals to 0.5 joule. Focused area, this is the area of the 0.05 mm square. The entire energy is coupled. Okay, this is the question. But what is the depth throughout it? Depth on the conductions. Uniform, uniform throughout its depth. So questions you have to, what will be the depth? So what is the depth? I mean, this depth you have to find out. This depth you have to find out. Okay. So start with the questions that total energy required for melting the aluminium. Okay. Total energy required for melting the aluminium. First of all, you have to calculate. Okay. So total energy, total energy required to melt the aluminum sheet equals to mcp delta t, mcp delta t plus latent heat. Okay, so what is the m? Total aluminum sheet mass, that is the rho into v. Okay, rho into v, rho into v volume. Okay, latent heat multiply, this is mass also. So m you have to common out, and cp value you know, it is given, and delta t value you know, plus lh latent heat. So put all the value. So rho is rho v, rho is given that 27 na, 2700 multiply v. V is the area multiply x. Okay, x you have to find out. Okay, so cp value, cp is 896, 896. cp is the 896 multiply delta t. Delta t is the 933 minus 303. 933, 933 minus 303 plus LH latent heat. Latent heat is in kg, kilojoule, 398. 398 kilojoule. Okay, 398. This is in kilojoule. Okay, but Cp is in joule, I think. Cp is in joule. So you have to convert it into kilojoule. Just I am writing here 0. This is kilojoule. All are in kilojoule. So if you calculate this, it will come that you have to just calculate, and that much amount of the heat, the total energy is 0.5 joule. Okay, 0.5 joule. Okay, and area is the 0.05 meter square. So all things are given. So area is the cross sections area is 0.05 square. A is given, energy is given, energy is given, that energy is 0.5 joule. So this equations, you just 0.5 joule equals to this bigger equations, and put the value A and find out the x value. This is your answer. So I have calculated. Okay, just you find out the answer. The answer will be, I have calculated, you just calculate. Sorry, uh, you just calculate the answer, it will come 3.85 mm. X value will be 3.85 mm. All value are given here. Okay, all value are given. You just calculate the x value. Okay, area is given. Area just you put in mm form. Okay, you will find out the 3.85. So your option will be D is your option. Okay, next. So our last questions, I'll solve last questions because it's 7:42. So question number 5. A 900 long steel plate is welded by manual metal arc welding process using welding current of 150 ampere. Arc voltage is 20 volt and welding speed is 300 per minute. If the process efficiency is 0.8 and the surface resistance of 36 micro ohm, the heat input in joule per mm. So long steel plate L equals to 900 and metal arc welding process. The current meter is showing here, current is 15 ampere and voltage 20 volt. Okay, the welding speed, that is the small v, 300 per minute. Okay, the process efficiency, or welding process efficiency is 0.8, means 80%. The surface and the surface resistance, here the resistance is 36 micro ohm. The heat input in joule per mm. The questions, your question, what is, you have to calculate the heat input, that heat input. Okay, so we know the formula. Okay, first of all, what is the heat? Generated heat, the generated heat and supplied heat. Okay, in terms of generated heat, heat generated equals to, so H generated equals to I into V. This is a very simple, current into voltage equals to power, that is the heat generated. So 150 multiply 20, that is the 3000 joule, 3000 joule per second or watt. Okay, so efficiency is given, the process efficiency. So process efficiency equals to, we know that the total heat supplied to the welded divided by total heat generated by the electricity. So H supplied divided by H generated. So H generated is high because I have told you that from the electric meter IV heat is coming, but during the welding process some heat will be lost out and less than IV heat is actually accumulating for the, or actually useful for melting the material. So this is the supplied heat, H supplied SUPP, this is S, and IV is the generated heat, H generated. How much I am generating from the electricity and how much I am supplied to the welding or welded portion or welded joint. Okay, so this is, so we can calculate that the heat supplied. So heat supplied, what, how much amount of the heat is supplying? Heat supplied equals to efficiency multiply heat generated. Okay, heat supplied to the weld. Okay, or effective heat or effective heat. Okay, so efficiency is 80%, multiply heat generated, how much I multiply V, that is the 3000 joule. So 2400 joule. Okay, 2400 joule per second. This is joule per second. But here the heat input, that is the heat input. Okay, the heat supplied means that the I am giving to the weld or heat input to the weld in terms of joule per mm. So joule per mm, that means the welding velocity. You have to come in the welding velocity. So heat input in terms of joule per mm. So we can write that the heat supply divided by welding velocity. Welding velocity V weld. So 24 joule per second divided by welding velocity is 300 mm per minute. So you have to convert it into second actually. Okay, so 2400 divided by 300. So 2400 divided by 300 second means 60. If you convert, so this is 480 joule per mm. 480 joule per mm. So our option B is the correct option. Okay, this is your answer. I have one question here. Okay, just you make screenshot it and you just solve. Okay, you just solve in your home. I am giving you the answer. Its answer will be 200. Its answer will be 200. This is the answer. You just solve in your home task. Okay, I think I have solved some advanced level numerical. That is the advanced level numerical 1, 2, 3, 4, 5, and home task 1, home assignment you can solve. And I have solved, or I have discussed the 10 basic questions. That is the 10 basic questions I have solved. Okay, and I think, and more importantly, you have to study the, I have also the total notes. Okay, from the starting point, from the starting, all the lecture is there. Okay, you can study. Do you have any doubt in this week 2 live session classes. Uh, what is the important thing? Just I want to address, that is the casting defect. This is very important. Casting defect you have to study, and welding defect you have to study. Okay, and all the things. Do you have any doubts? You can ask me. Kausik, Umer, Syed. Sir, week 1 assignment last questions. What is the questions? You just share with me, or you can mail me. I will discuss. I don't know what is the last assignment questions. Mail ID. Okay. My mail ID is, just I am writing here. SUBRATAK underscore MAITI @PE dot IITR dot AC dot in. Subrata K underscore Maiti @P dot IITR dot AC dot in. You can mail the questions. Huh. The amount of machining allowance depends on the material and overall dimensions of the job, type of the casting process used, area of applications of the product, all of them. The machining allowances depend on the, what is the machining allowance? First you have to understand. The machining allowance means this is not the shrinkage allowance. Okay. Type of the casting processes used. Okay. What is the type of casting processes you are going to use? Area of applications of the product. Area of application of the product, it may also happen because you need some smooth surface or machining grinding type surface. Material and overall dimensions of the job, this is also important. I think all of the above it should be. In solutions, option 1, sir, the excess amount of, you just ask me, you were writing na.
Sir, good evening, sir. Sir, I'm
ha
audible?
yes, Parveen ji.
Sir. How are you, sir?
Yes.
Sir, actually, we put all of them, but in the solution, we got answer as first one alone, sir. So that
First one.
we got a wrong answer for the 10th question.
Okay,
Uh,
okay.
but we assume that all the things may be influencing on for that one.
Yes, yes, I understand. But
Okay, okay.
sometimes you have to understand. But they're giving the more importance to the first
Yes, sir, yes, sir.
material and overall
But
dimensions of the job.
yes, sir. But they're asking generally, yeah. So we couldn't find it clearly, sir. So that's why I'm having
Yes,
this
yes,
problem.
I understand. Yes, understand.
Okay, okay, sir.
But first answer has the more dominance.
Yes, sir.
That is the
Yes, sir.
material and overall dimensions. Actually, the
Yes, sir.
machining allowances is given for the just to, why we will machine, just to give the accurate dimensions. That's why we will machine the after casting. That's why
Okay.
their A type of casting process is not so much useful. Actually, I told you because the type of casting process, because you are adding a runner, riser or not. These things, it depends. Okay. Area of the applications of the product, that means first one is the most priority, I mean dominance factor, obviously, I
Yes, sir.
should say. For the dimension accuracy, we give the machining allowance. Okay. Okay.
Yes, if possible, just reconsider, sir, and then share the answer with us.
Yeah, yeah,
No
understand.
problem, sir. No problem.
Sometimes it happens, no issue.
Yes,
But
yes,
the main thing of the machining allowances, just why we will machine,
yes, sir.
because for the smooth surface or accurate dimensions. That's why we'll machine, na? Okay.
Yes,
Or removing the extra portions, that like the gating system, riser, runner, all the things you have to remove out or machining out. That's why. Okay. Here machining means that the surface finishing. That's why they have tick the first answer, I
yes.
think. But machining also consider during the machining time you have to remove the gate, you have to remove the all the extra part, runner, riser, all the extra part you have to remove by machining. These things, this is okay. Sometimes some questions it will happen, but
Okay,
basic things is that machining allowance means that the for accurate dimension, overall dimensions.
okay, sir. So we will keep this answer for further reference also. Thank you, sir.
Okay, okay.
First option. Okay, sir. Right.
Huh.
Okay.
Oh, today I have whatever I have solved some numerical. I think it will helpful for you and all the students. I
Yes,
think you are understanding the numerical.
yes, sir. For a final exam also, numerical will come more or less. For
Yes.
final exam, numerical will come more questions or
Oh
30
yeah,
percent.
yeah. Actually,
Because, because it is a 4 week course, that's why I'm asking, sir. My students thought it is a 4 week, so it may be a theoretical one.
in your questions, in your NPTEL examinations, not so difficult questions will come. Like these questions will come actually. Okay, but I
Okay,
am solving some difficult questions, some easy questions. Okay, but for your better understanding, just I am taking some advanced level questions. But these type of questions, I think questions will not come, but some basic questions will come actually in your question examinations.
yes, sir. Thank
Not
you,
so
sir. Thank
not so lengthy questions will come. Just if you have some basic understanding that whatever I solved the basic questions under the basic questions, this type of questions will come. Very short questions, not lengthy questions will not come.
you. Yes,
Yes, yes.
thank you, sir. Thank you, sir.
Thank you, thank you. Kausik Pal, are you there? Yes, yes. Thank you, thank you. Okay, I think this is the end of the today's lecture. Okay. Uh, just I am uploading the video. You can follow the video whoever have missed the classes. Okay. Thank you for today's attending the lecture. Okay.